Welcome to the lecture on fluid flow fundamentals. So, as we know that we will be dealing with the flow inside the tundish, and this flow is of the molten steel. So, we need to have the proper understanding of the flow behavior inside the tundish. Molten steel will be flowing and then accordingly, I mean when it is flowing inside the tundish. So, there will be many phenomena which will be occurring inside. There will be flow around the corner in the tundish, then during that process there may be flotation of inclusions. Then you will be associated phenomena like there will be heat transfer from the walls and from the top. So, we need to have the proper understanding of the fluid flow as well as the heat transfer phenomena. We should have some basic understanding about the fluid flow phenomena and how to model it. So, what are the different terms which we need to know, what are the fundamental principles, what are the governing equations, all is needed to study the behavior of different processes inside the tundish. So, in that line initially we need to have the understanding about the fluid flow fundamentals, and in this lecture we will have some light over the initial fundamental understanding about the fluid flow phenomena. So, laws of fluid mechanics govern the flow of metal, entrainment of gas and slag, the movement and flotation of non-metallic inclusions, etc. So, as we discussed that here in all these cases the laws of fluid mechanics which will be governing the flow of metal, they will be important, and that is why we need to understand the fluid flow behavior, especially if you talk about the tundish. So, in the tundish you have different regions. There is a region where the liquid metal is coming from the ladle, and then you have the remote regions also. So, in most of the cases generally the tundish flow is considered to be turbulent. So, we need to also have the understanding about the laminar as well as the turbulent regions. What are the laminar regions, how there is turbulence region defined. We need to have understanding about the characteristics of the laminar flow as well as the turbulent flow, because there will be a mixing which will be going inside the tundish. There may be different kind of processes, heat transfer, there may be one phase, two phase or so. So, actually we need to know about the fluid flow, turbulence, heat transfer and all that. So, during this week we will be talking about the fundamentals about the fluid flow. So, coming to the fluid flow regimes. So, as we know that when we talk about the fluid flow, then the flow regimes are basically classified as either the laminar or the turbulent flow regime. So, as we see that when we talk about the laminar flow, in that the layers of fluid will be sliding over one another without any macroscopic mixing or even the intermingling of fluid in the direction perpendicular to the fluid flow. So, that is normally the laminar flow. So, in the laminar flow, if you talk in a very rough sense, so you have the layers which will be moving over one another. So, there will not be any kind of vortexing, there will not be intermingling of fluid in the direction perpendicular to the fluid flow, like when you have suppose you have the conduit. So, the layers move one over other. So, this is a kind of flow, that is your laminar flow. Whereas, and in this case there will not be intermingling, as the definition tells, that there will not be intermingling of the layer which is one of other. So, they will not intermingle with one another. Whereas, in the case of turbulent flow, that is not the case. In the case of turbulent flow, macroscopic mixing will be taking place between fluid layers or portions of fluid over relatively long distances. So, in this case you will have the macroscopic mixing taking place, and that will be also taking place between the fluid layers or portions of fluid over large distances. So, you will be talking about those distances or length scales or so. So, in that we need to understand about different type of models which should be talking about these turbulence behavior, and then its associated effect on the on predicting the output parameters. So, we will have the discussion about the turbulence itself in the coming week. So, there we will be talking about these over relatively long distances. So, how these layers are interacting, how there is intermingling, and how these distances are taken into account. So, these things are discussed. As you know that the demarcation between the turbulent flow and the laminar flow, it was done by it is done by a very renowned number, that is Reynolds number, and it is by the very renowned researcher scientist Osborne Reynolds. So, he devised or he has given this number that is known as the Reynolds number. So, this is the criteria for for differentiating the laminar flow from the turbulent flow, and Reynolds number will be defined as L V rho upon eta. So, many a times we write rho V d upon mu or eta, whatever. So, in this basically we take this L as the characteristic length of the system. So, it is normally like the diameter of pipe when we are talking about the pipe flow. Similarly, you have V. So, V is the average velocity of the fluid. Then you have rho and eta is there. So, rho is the density of the fluid, and eta is the viscosity of the fluid. So, depending upon, so once you have any geometry or container in which there is flow going on. So, using this correlationship you will find the Reynolds number, and if this Reynolds number is more than certain critical value for a particular configuration of vessel, in that case it is said to be turbulent, or if it is less than that, so it will be laminar. So, there will be transition from laminar to turbulent, and that will be defined by that will be at a limit to that number, that is known as the Reynolds number. So, for the pipe flow it is given by 2100. So, so that may be different for the different type of cases, and similarly we can have surface flows. So, and there this number will be different. So, similar, so that way when we talk about the flow of molten metal even in the tundish also. So, in that case we can very much find whether the flow is turbulent or laminar depending upon the value of these Reynolds numbers. So, Reynolds number. Now, next thing which will be further required to know to us. So, you will have the transition from laminar to turbulent is characterized by dimensionless quantity known as the Reynolds number, that is what we have seen, and this will be this transition will be dependent on the boundary geometry of the system. So, they will be basically partly to the arbitrary nature of the characteristic length L and partly to the inherent differences in the flow pattern. So, they will be dependent upon that way. So, depending upon the geometry you will have the maybe the different value of the Reynolds number which will be demarcating the place I mean and the point at which there will be transition from the laminar to the turbulent region. So, then we need to know also a very important property of the material, that is viscosity, and that is basically defined by the law. So, this law is the Newton's law of viscosity. So, you will have as we see that there will be velocity gradient, and that will be creating the shear stress. So, so what was seen that the shear stress which was plotted against the velocity gradient. So, it was seen to pass through the origin, and that was by an experiment, and this experiment was basically that you had a stationary plate. So, this was the stationary plate, and you have fluid in between, and this is a plate which is this is allowed to move. So, this is a moving plate, and similarly you have this as the stationary plate. So, initially upper plate is this is a stationary. So, you will have if you see that this is your x direction and this is your y direction. So, here you have y equal to y and you have v equal to 0, and here you have y equal to 0 and v is v. Actually, you are moving this plate with velocity v. So, and if you assume that there is no slip in this case. So, what will happen that the layer of fluid which will this will start that moving with the velocity v. So, that this is in between there is fluid. So, once you are moving it, the fluid which is in contact with this moving plate, it will also start moving with velocity v. So, this is stationary. So, it will have the same it will be stationary itself, but the fluid which is here they will start moving with the velocity v. So, you will be seeing the a kind of velocity gradient as we move in this direction. Now, here, so the lowermost this lowermost this fluid layer, it will be gradually transferring this momentum to the upper fluid layers, because upper fluid layer, although it is in contact. So, they will because of the movement, it will be transferring this momentum to the upper fluid layers, and initially there will be some unsteady kind of situation, and then you will have, after sufficient time, you will have a steady state which is reached, and then you can have this velocity profile. and at that time the fluid velocity will not change with time. So, this kind of velocity profile you will be getting it. Now, in this experiment what is observed, that you will have when you have the attainment of a steady state, in that case a force must be exerted on the lower plate. So, to keep it in motion. So, you will have to have this a force needs to be exerted, and Newton has found that this force per unit area of the plate, that was found to be proportional to the velocity and inversely proportional to the spacing y. So, what was seen that the force per unit area, so force per unit area of the plate is proportional to velocity v and inversely proportional to the spacing between the plates. So, that is what was found by Newton. So, what he found that F by A, so this is proportional to V by Y. Now, you will have to give so A is basically the surface area of the plate, V is the velocity, Y is the distance in y direction. So, so if you put the constant of proportionality, F by A will be eta times V by Y. So, this eta, that is, so F by A, if you look at force per unit area, so that will be talking about the shear stress. So, this is the shear stress. So, F by A will be the shear stress at the interface. So, this is known as the shear stress, that will be at the interface between lower plate and adjacent fluid layer. So, so accordingly what you see that the shear stress that is basically what you see. So, you can express it as the velocity gradient. So, if you talk in terms of the velocity gradient, so change of velocity with respect to the y. So, what we see that if you denote this as the tau yx and this is as dvx upon dvy. So, by dy basically change in distance that is y. So, you can write if you write in the differential form. So, you can write in the differential form as tau yx, it will be minus of eta into dv upon dy. So, as because as you are increasing y, the change in velocity is negative, that is why when you are writing in the case of differential in differential form. So, you see that this is tau yx, that is known as minus of eta dv upon, so dv x upon dy. So, this rule is known as the Newton's law of viscosity, because it is defining this term eta that is your viscosity. Now, in this term you see tau yx. So, this tau yx if you see, so your tau yx becomes minus of eta dvx upon dy. So, your you have y as well as x. So, this will be in tau yx, the y will be the direction of momentum transfer. So, in tau yx, y is the direction of momentum transfer, and x is the direction of fluid velocity. So, so that way we are writing this tau y x. Then eta is known as the coefficient of molecular viscosity. Or we also call it as simply the viscosity of the fluid. Then and dvx upon dy. So, this is known as the velocity gradient. As because the eta has to be always positive. So, this term we are putting the one negative sign, and that will be having certain meaning, because that has to be having the positive value always. The viscosity value cannot be negative. So, what we see that this viscosity, that is the molecular viscosity, and it is because of the molecular exchange of the momentum taking place in this kind of flow. Now, this is normally in the case of laminar flow, where we assume that there is movement of layer one over other in a laminar manner. Now, the liquids which obey this law, where the shear stress will be proportional to the velocity gradient. So, they will be known as the Newtonian fluid, and these fluids like water or so, or molten steel or so, they are at that temperature, molten steel. So, they are considered to be the Newtonian fluid, whereas there are fluids which do not obey this law. So, in those cases there is no linear relationship, or there may be different relationship than what is being observed by this kind of by these fluids, Newtonian fluids. So, they are known as the non-Newtonian fluids. So, the aim is basically to have the prediction of the shear stresses, and because so that is why now in the case of our analysis, mostly we will be dealing with the Newtonian fluid only. So, mostly we will have the dealing with these principles. Now, when we will see that we are not only concerned with only this molecular viscosity, but as the flow in the tundish is turbulent. So, in that case you are not assured only, and you are bound to have the intermingling of the fluid layers. So, you will have not only the momentum exchange across the layers only. So, that may be over the large distances. So, you will have other viscosity component also because of the turbulence, and that is known as turbulent viscosity. And then you will have the effective viscosity as the sum of these two. So, that is what some idea we had got in the earlier lectures also. So, in those cases we will have the prediction of that turbulent viscosity, and that we will study when we will talk about the turbulence. So, how that is taken into account. So, so that will be seen in our coming lectures. So, if you talk about the viscosity, so viscosity has a unit, and that is you have many kind of, either you have SI unit, or you have the in CGS system also you may have the Poise or Stokes or so. So, if you talk about the unit of viscosity, so what we do is in SI unit tau has the unit of Newton per meter square, and then you will have this is meter, and this way you have meter per second. So, accordingly you can have the unit of viscosity, and that is kg per meter second. So, that is your unit in the for the viscosity. And if you go for the CGS system, then it is the poise. So, 1 poise will be 1 gram per centimeter second. So, you will have either unit of kg per meter second, or you may have the gram per centimeter second. So, that is 1 poise, and this is 1 Pascal second. So, if you so this is Pascal second, and this is you will have the poise. So, if you see that 1 P 1 poise will be 0.1 Pascal second. So, that way this relationship also is coming up for the unit of viscosity, and unit of viscosity it has some standard value at some standard temperature and pressure. Now, we have another term with viscosity. So, in the case of engineering analysis, what we do is we normally define the viscosity also in terms of viscosity to density ratio. So, for a fluid, when we take the ratio of the viscosity to its density, so that is known as the kinematic viscosity. And this kinematic viscosity is represented by the term nu, and its unit is actually meter square per second. So, in the case of SI units, it will be meter square per second, and in CGS system it is centimeter square per second. So, that is the Stokes. So, that way you have the other units for the viscosity itself, that is known as the kinematic viscosity. So, this is about that property of the fluid. Now, coming to the dimensionality of the flow. So, if you talk about the present case, so if you see that the velocity will be changing in one coordinate direction as you are moving in the y direction. So, your velocity seems to be changing. So, that is basically one dimensional flow. So, velocity if changes in any one coordinate direction only, then it is considered the one dimensional flow. Similarly, if the velocity is function of x and y coordinates both, then the flow is said to be two dimensional. So, if you talk about the boundary layer, so if you see the momentum boundary layer, so in that what you see that velocity will be changing, and if you look at the so what you see that in this case, earlier case, what you have seen that velocity is only changing in the y direction. So, this is as you y changing. So, that is why it is said to be one dimensional. Now, if you talk about a momentum boundary layer, now in that case what happens that in the case of boundary layer you might have experienced that your velocity profile goes like this. In the boundary layer it will be changing. So, your if you see the velocity, it will be changing in because of the x and the y in both the directions. As you move the here, so your it is changing. So, in those cases what you see that your velocity will be function of the x and y coordinates, that will be changing. So, that is why the flow is said to be the two dimensional. Similarly, if it is dependent upon the all the three coordinate directions, then it is said to be the three dimensional flow. And normally when we talk about the flow inside the tundish, then it is the three dimensional flow. So, while analyzing we will have to have this in mind that it is one dimensional, two dimensional or three dimensional flow, and accordingly we will have to do the analysis of the flow. Then comes the mode of momentum transport. So, basically there are two modes of the transport, momentum transport. One is momentum convective transport, and another is the diffusive transport. Now, when the momentum transport is in the direction from higher velocity layer to a lower velocity layer. So, as we have seen in the earlier case, your the momentum transport is from the lower layer to the higher layer. So, you will have the velocity at lower layer you have higher velocity, and at upper layer you have lower velocity. So, when you have the momentum transport from the higher velocity layer to lower velocity layer. So, in that case your momentum transport is because of the diffusive diffusion. So, that is known as the because of the viscous effect. So, you have a viscosity coming into picture. So, it is because of that mechanism. So, that is why we call it as the viscous or diffusive momentum transport. Now, when your momentum transport, so that is your the convective viscous or diffusive momentum transport. Now, if your momentum transport is due to the motion of the fluid itself in the flow direction, then it is known as the convective momentum transport. So, if you look at the this viscous or diffusive momentum transport, so in that basically the molecules will be crossing the layers, so that will be as per you have the molecules like you have the top layer molecule is there. So, and below that you have the molecules. So, this way you have layer of molecules, and you will have the momentum transport will be using this mechanism. So, that is there in the case of so this is because of the viscous property. So, that is why it is viscous momentum transport, whereas if you see that when you had the two plates and one is in motion, and when your so your if you see that when your this was the velocity profile which was seen in the case which we studied. So, the viscous momentum will be in this direction. So, that will be transferring the momentum, or momentum transfer will be in this direction. Now, if it is because of the velocity. So, if it is because of that velocity, so the velocity is in this direction. So, that is known as the convective momentum transport. So, the rate of convective momentum transport that will be mass into velocity by time. So, if you look at the rate of convective momentum transport, it will be rho v x square a. So, your that a is the cross sectional area. So, here this is the cross sectional area perpendicular to the flow direction through which the density, the fluid of density rho is flowing. So, that way we are finding the rate of convective momentum transport. So, so accordingly you can you can have the understanding about these properties. You can have the study of other fluid properties also, like surface tension and other things, which will be used in our lectures to come. Thank you very much.